we start, and I think the good point to start is an introduction. Could you talk a little bit about your background, what you were doing in the past, what are you working on right now?
Okay, thanks, Sergey, for having me. My name is Yehuda Naveh. Basically, I'm based in Israel. I was born here, raised in Jerusalem, Israel, also studied there at the Hebrew University, have done my 3 degrees over there, physics and math, and then specialized in experimental physics for my master's and theoretical quantum physics for my PhD. And after that, I moved on to Stony Brook University outside New York City and have spent some as a research scientist, some 4 years also doing theoretical quantum physics. And then my main tenure was at the IBM research lab at Haifa, Israel. It's in northern Israel, and incidentally, the second largest IBM research lab worldwide. And over there, across my tenure, I was basically at the interface between computer science, mathematics, and theoretical physics, doing all parts of the basic logic aspects of classical computers, but in the last 5 years or so, of quantum computers, which surely needs some strong theoretical physics backgrounds, and dealing a lot with noise processes of the computer and ways to simulate a computer with a large team at IBM, obviously part of the worldwide activity of IBM Q. And at some stage, together with my 2 partners, I joined them to form this new company, Classiq.
Okay, that sounds very good. And if I'm not mistaken, right now you're working on the quantum software field.
Yes, this is correct. So I'm the CTO of Classiq, and the reason we formed this company is that there is a very wide gap, I would say, right now between the ability, to simply write quantum software or quantum algorithms, or even to design an algorithm which will do your need, and the actual hardware. So I think that anyone in the field notices this gap between the abilities of the hardware and, on the other hand, the difficulty or the hardness to write useful algorithms which will run on the quantum hardware.
Yeah, and the quantum software field, when do you think it really start appearing as not just a thing for laboratories and research center, but really something more industrial and people really need application? It didn't start so long time ago, right?
No, I think it is a very new activity. I think it is even right now in the state of formation. If we look in perspective, say 20 years from now, people will look backwards. I think we are still in the midst of defining what is actually quantum software.
And actually, maybe my following question will be, so what is quantum software? What we're actually working on then?
Okay, so there are several ways to answer this. Essentially, quantum computing, just like classical computing, by the way, you can view it as a physical experiment. There is no use for a computer which is only on paper in terms of computer science. Underlying is the logic, but the logic must be realized on some hardware, and this is where the physics comes about. So in classical computing, we are already very far away from thinking of a classical computer as a physical experiment, but at the end of the day, this is just what it is. In quantum computing, we are now in the stage of transforming from thinking of a quantum computer as a physical experiment. And when we do this, when we think of a quantum computer as a physical experiment, all we need to care about is the microwave pulses or the laser pulses, which incite or give inputs to the actual experiments. So we are now transforming in how to formalize those microwave pulses or the physical interface with the qubits, with the computer, into some language and forms that people from computer science are more used to. So at the lowest level, as I said, we have the microwave pulses, but the more interesting level is what we call the universal languages or universal gate languages. So people have shown with some beautiful theorems that if you limit yourself to some very limited set of, I would say, of activities on the computer, of commands to the computer, you can essentially, in some sense, create any experiment you want, or any input to the computer can be limited to some very small number of universal, what we call gates, universal commands to the computer. So this is the interesting layer. This is the layer where the physical experiments becomes a computer science, a computer science way of thinking. But on top of that, after we forget about the theory, those universal gates alone are not enough because they are not useful in the way of when you want to think practically. How would I write a software or a computer algorithm or a computer program, whatever you want to call it? How will I write it in a way which will practically make the computer do what I want? This is the higher level of interfacing with the computer, and this is where we, as a research community are right now.
Yeah, so as I understand, if I understand you correctly, what you're saying, there is a hardware layer when it's people really talking about laser pulses, some, let's say, radio frequencies, but then there is next layer which bridging, let's say, this hardware to the software, and people on the high end should really work only on the, let's say, software development and don't think about this laser pulses and really technical stuff. That's what you're saying, right?
Yes, exactly, and this is the challenge. And there are some mathematical, theorems on the way which give us hope that this is possible.
And so what's then the challenge for the quantum software developers and as a whole field, as a community? It's really to develop a nice communication between hardware and users.
Yeah. So luckily we have the classical analogy here. When people first designed software or thought about software for classical computers, they did not have any analogy, and they needed to write everything from scratch, from their thinking. And that's, by the way, why it took such a long time. Right now we have the classical analogy, which we try to transform into the quantum arena. So the answer is yes. The person who wants to make use of the computer, to make something useful from a quantum algorithm, needs only to think about what are the algorithm's goals, what would he or she want the algorithm to do, how would the algorithm be designed. And some automatic layers in the way to the actual hardware should do the actual work of translating into the hardware input, which are radio frequency pulses. So those can be synthesizers, which take, the model that the user thought what they wanted, and can be compilers, which take, command level instructions to the computer and make them optimized and translate it into the specific hardware. But all this should be automated just as it is in classical computing. The user, the algorithm designer, needs to think only about what he or she wants to achieve with the computer.
Yeah, and if I understand you correctly, then your goal is to really help the user to talk to the hardware, right? That's pretty much is the goal of your company for the field. Am I correct?
Yes, that's actually the goal of anyone dealing with software. The goal specifically of our company is to create another level of automation, which makes it more handy to the user. So let me say maybe one word about the current status of algorithm design for quantum machines, of course, for quantum computers. There are two ways today to write algorithms, either going by gate-to-gate level, the universal, I would say, constructs for a quantum computer are what we call quantum gates. So you could write your algorithm at a gate-by-gate level. This would be in somewhat similar to writing, a large program, say a Word program or whatever, by the individual assembly level constructs. And in addition to that, there is today quite, I would say, a large corpus of building blocks, pre-existing building blocks, or even algorithms that the end user can use. So the end user has in their arsenal software packages which allow them to put gate by gates, in addition to taking pre-existing building blocks which people have already done by the gate-by-gate constructs, and also tune some pre-existing algorithms. This is the situation today. What we don't have is some higher level way of writing how we want the quantum algorithm to function, how we want it to work, without using any pre-existing building blocks or algorithms that someone else designed for us. Saying it in a different way, if I wanted to construct today a new building block, a new quantum building block, I would need to design these building blocks on a gate-by-gate basis. And what our company aims to achieve, and we have already quite a few successes, is letting the user define what they want the algorithm to achieve or how they want the algorithm to function, and then to completely automatic by deep technology, by constraint satisfaction technology, take those constraints of the user and create out of blue sky a quantum algorithm, a gate level quantum algorithm, which can go to the quantum computer, but without the touch of a human being. Everything is done automatic under the covers.
That seems quite complicated in the sense that you have to think about new technologies because users, they have, let's say, problem to solve, and hardware has its own, let's say, pulses and IR frequencies. So the goal is to really bridge it and do it automatically.
Yeah. So we bridge the gap between, what the user states and a universal quantum circuit written at what we call the gate level. There is another level of automation which is very mature and people have already written it in many companies, which is the compiler, which takes the gate level circuit and compiles it into the radio frequency pulses.
Yeah, and maybe another question. So right now we have, let's say, in the terms of hardware, different platforms. We have ions, superconductor circuits, photonics, things like that. But this hardware, they're a bit different in terms of functioning. So when you're programming the software, do you keep in mind that there are different hardwares?
So there are two answers for this. First of all, one of the most marvelous things that the quantum community has done early on is to define a universal gate level language. And in a sense, you could think of it as if all, suppose, classical computers would have the same assembly language. Then at the back end of the compiler, all compilers need to compile only to a single universal language. And then you can take this language, each of the hardware provider can take this universal input and translate it, whether if it's on, like you say, on a superconducting chip, to translate it into 10 gigahertz microwaves. If it is on a neutral atoms or ion atoms, to translate it into laser pulses. But the input, the low-level input, is in a universal language. This is a marvelous standardization that the quantum computing community has achieved. So all we need to do is automatically translate the user's directives or the user's description, the functional description of the algorithm into this universal language. After saying that, if we know in advance on what type of hardware the algorithm is going to run, then we can add optimization to what we are doing already at the front end and not only at the compiler end. So it is two different use cases. In some cases, a company or a person would come and say, They know on what type of platform we want to run, and then we can take this into account. But in a very different use case, people many times tell us, because we are at the experimental phase of quantum computing, that we want to experiment with many types of hardwares, many types of platforms. In this case, we produce only a universal gate-level circuit, and then the hardware, each of the hardware providers also provide their compiler to take this universal gate-level algorithm and translate it into the correct pulse implementation.
Yeah, and I think right now there is another maybe $1 billion question, which is when these things really become practical, because everybody wants to solve, let's say, practical problems with quantum computers, and of course it's a question for the hardware and for the software. So what do you think it will? What type of practical problems we actually can address with quantum computers?
Yeah, so like you say, it is $1 billion question. Nobody honestly knows the answer, but I can give you several, hints about the trend.
Please.
First, you are absolutely correct that it is a dual endeavor. Both the hardware needs to advance, but also the software needs to advance. We are very far from having a mature corpus or set of quantum algorithms. So even if the hardware is here, there is still a lot of work to do in terms of finding, the killer applications and the killer algorithms for the hardware. Now let's look about the hardware. There are two stages. There is the fault tolerant stage, which people believe, and myself also, will come only after we will have robust error correction. So we don't think that we will have any time in the reasonable future qubits which are noiseless. The way to create, quote unquote, noiseless qubits is by logical operations, which in a sense means quantum correction schemes, which means that for every logical qubit in my algorithm, I would need an implementation of around 1,000 qubits in my hardware, and all those 1,000 qubits will realize a single logical qubit. This is quite far away. It's, say, at least a decade ahead from us right now. On the path to this, and by the way, a decade is not that large time, so we should prepare for that as well. On the path to it is what we call the NISQ era, the noisy intermediate scale quantum devices, where people strongly believe, and myself included, is that even before we have fault tolerant implementations for, exact algorithms, quantum computing in some cases provide such an enormous power compared to classical computing that even better heuristics and even better heuristics under noise, as long as they are quantum heuristics, will create a real and great advantage in industrial situation. Now the question is, when will this come? The noisy devices, when will they be more advantageous? So if we look at the trends, and the trends are like that for, I would say, more than 4 or 5 years right now, is that both the number of coherent qubits on a chip, on a device, and the quality of each and every qubit grows at a very large pace. And if we look at technological forecasts from the large companies, we expect this pace to continue. The reasonable thing to say is that once we have around 1,000 qubits, which coherently work together on a chip, even if those qubits will still be noisy and the correct errors will not be, purely corrected, it will give values in several industries. And if we look at the technological roadmaps, this is about to be with us in around between 2 to 4 years.
Yeah, so what you said one interesting number. So in terms of software, when we want to run important algorithms, we need at least, let's say, 1,000 qubits with error correction. That's what you said.
Yeah, I think we will start seeing advantage already with 500 qubits with no error correction. With 1,000 qubits with no error correction, we will see it across several industries, this advantage.
Yeah, and let's say we have already like an idea which problems should be implemented first, which problems should be addressed with this, let's say 1,000 qubits? Is it there is like an idea?
So I think the most direct problems to implement on quantum computers are the ones taken from nature. They typically go under the name or the umbrella of quantum chemistry. The reason is that there is a direct way of translating a quantum chemistry question into a quantum computing scheme. And those questions are inherent, well, obviously, to drug discovery and other biological aspects, but also to material sciences, to better fuels, to less pollution in fuels, and so on. Those problems are quite straightforwardly directed into quantum logic, but on the other hand, they are very, very antagonist or very difficult to translate or impossible to translate into classical logic. So even for the most simple problem in quantum chemistry, if you try to simulate it on a classical computer, you are just at odds. You have no chance. And when I say classical computer, I don't mean my laptop. I mean, computers like in Los Alamos or Lawrence Livermore connected together. So this is where the widest gap is between, useful industrial applications between quantum and classical computers. People took this analogy and tried to, expand it in terms of what nature does to things which are outside of nature. And then there are all types of difficult optimization problems which are also reasonable to assume that quantum computers will be stronger there. The reason that there may be doubt over here is not that quantum computing will not be strong enough, but whether do we really have hard optimization problems which are so critical for the business that classical computers still cannot solve it. Let me maybe reiterate that in quantum chemistry, it is clear that we have critical problems that if we could solve, our, everything, humanity and business would be so much better, because today when you try to understand the interaction between two molecules, for example, an antigen and its antidote, it is just impossible to simulate on a classical machine, and you need to do a lot of laboratory work. If we had this ability, we automatically, will just enormously benefit from it.
Yeah, and as you mentioned, probably quantum chemistry is just one application. Of course, we can dream right now about other application. Of course, I've heard words like business portfolio optimization, and but probably this type of problems, they need more qubits, more complicated algorithms. So they will come in the future, right?
So they will come in the future. And in fact, many of those aspects like portfolio optimization and asset pricing, if we remain or risk analysis, if we remain in the financial industry domain, or maybe optimization of autonomous vehicles on the road, if we go into the automotive domain, or gate assignment to airplanes, if we go into air and travel domain. All those critical business problems have some aspects which are similar to quantum chemistry if you know how to translate your problem into an optimization problem, into a quantum optimization problem. So it is not that far away. Once we know how to solve the quantum chemistry problems, it is not that far away to find reductions from other industry problems into the quantum chemistry problem.
Yeah, and once we're talking about these complicated problems, what is the main, let's say, bottleneck? What is the main challenge to address with quantum software? Because on quantum hardware, I kind of understand we need more qubits, we need them more reliable. But what's the main challenges to make these software algorithms in terms of software?
Okay, so to be very blunt, if we look at the situation today, we have 4 proven algorithms that work. I can just count them because it is only 4. We have the Shor algorithm, which factorizes numbers. We have the Grover algorithm, which searches for a singular solution. We have the HHL algorithm, which solves some very specific set of linear equations. Well, I would say a sparse matrix, but it is very specific, the case where matrices are sparse. And we have Hamiltonian propagation, which solves, in some sense, quantum chemistry problems. Other than that, we don't have any proven algorithms. Compare this to the classical situation where you have an algorithm for anything, for sort and for merge, and for anything you have an algorithm. We should bridge this gap. The quantum logic is very difficult, to comprehend and to have it as a working tool. It is difficult to reach for, say, a 15-year-old smart person and tell them just write quantum algorithms as they do every day, in school, just using their smartness. There are things to learn here, and the intuition is very, very different from anything else that we know. The challenge for companies like us is to take all this very complex thinking about logic and all this very non-intuitive way of writing an algorithm, a quantum algorithm, to encapsulate it inside, I would say the automation layer, or to encapsulate it behind the covers, and to provide an intuitive front end to the user so they could write any, algorithm within some limits that they can think of, and let automation do everything else. Let automation deal with the linear algebra behind the scenes. Let automation deal with the entanglement and the superposition and other things taken from the quantum realm. And once this is done, then there is all hope that people could come up with useful new algorithms and heuristics, because the manual work, the difficult part of the quantum logic, will be done by what is, suitable for doing this, which is a machine. And all the creativity will be left with, the person.
Yeah, and you already mentioned that there are 4 algorithms which are really proven to be really good for quantum computing. And I think like the earliest was written, I don't know, like 30 years ago, 20 years ago. And it's still people didn't come up with new algorithms. It's only 4, because I guess it's more and more people working on them, but it's only 4. And you said it's really complicated problem. You have to think, you have to different your logic. So could we expect new algorithms like that?
So my belief is certainly yes, and this is because 2 reasons. First is the incentive part. Once we have quantum hardware, we will see a lot more smart people thinking of that. But that's not enough, because, as I said, it's very non-intuitive. Quantum algorithms are just linear algebra, but they are complex linear algebra. And it's very non-intuitive to think in those terms, in those low-level mathematical terms. So the second reason why we will see more and more algorithms is because companies like us will advance in taking, the manual aspects or the linear algebra aspects from writing quantum algorithms, will put them under the cover, will form an automation which does the linear algebra by itself, and provide the user with the handles in only writing what would the user want the logic to do, and not how to do it.
Yeah, and right now we're talking about these complicated algorithms, and I believe that right now more and more people join these efforts, and there are more and more startups, big companies, let's say, investing money in that. So do you feel like there is more, let's say, efforts and energy putting into developing quantum algorithms? So is it community growing, and you feel that we're improving faster?
Yeah, absolutely. In terms of numbers, absolutely. There were any software computing companies, say 4 or 5 years ago.
Yeah, and so how are you sort of separating tasks? Because so let's say we're talking about quantum software development, right? So each startup picks up its own problem and then trying to dig deep and improve it for the whole community, and then we sort of put efforts together and then we create a nice software for quantum computers. Is it sort of like a gist of it?
Yeah. Let's not forget that that we are companies in the sense that we want each of the commercial companies wants to
Create a product pretty much.
to have a place in the market. So in this sense, there is some competition, and each company brings its value. Some companies are more like services companies, which have very smart people who write algorithms for others. Some are consultation companies, and some, like ourselves, are tool-based companies, which provide some tool or another. But having said that let's not forget that we are in a business situation. Having said that, I think I'm not exaggerating if saying that the quantum community, even the business quantum community, is the most open community in anything I've seen. And everyone in the community, well, first we know each other personally. It's a small community, and all my friends work in different companies, and we talk to each other. And the situation is the same in other companies. We love to share. We love to talk with each other. We love, to synergize in the sense that if I do something which can make another company improve the way they are doing because I am in a different place on the stack, I will do, and I will share it with them, and vice versa. We go to all conferences together and we talk with each other. One of the things I love best about doing quantum computing is the openness of the people working in it.
Yeah, I agree. I agree with you and I think part of this coming from the fact that lots of people coming from the academic background and academia, it's sort of natural to share. So that's why people quite open. And I think it may be a good point to switch gears and talk about your startup, Classiq, if I'm not mistaken. So how did you come up with this idea? Why you decided to start a company?
So it was simple. We understood where the gap is between. We had a vision to look into the future. We saw that we believed in quantum hardware in all its implementations, whether superconductors or ion traps and so on. We believed in it. We looked into the future. We saw that within 2, 3, 4, or 5 years, this is going to be a real thing. And we are software persons, and we understood that the software is required and that people could not interface and do the amazing stuff on those machines if they won't have the software layer.
Yeah, and you're coming from the, let's say, industry part of the problem because you were working at IBM, I think, for 20 years, if I'm not mistaken.
That's correct.
So so you decided because you were working in IBM, and in IBM they already started, let's say, putting efforts in quantum computing, because they said, okay, there is a gap, let's just jump into it, right?
So actually, from from historical perspective, it was not quite so. My two partners, Nir and Amir, they started looking in it much before I even thought about it, and they understood this vision of quantum computing is here to stay and what is needed. And at some stage they started asking me questions, but in many ways, in many senses, I joined them on this train.
And like, do you already have, let's say, in mind your first customer? So maybe you already have a customer. So what type of product and services you're going to? Of course, you already talked about it in the beginning, but maybe can you summarize it again, please?
Yeah. So in terms of existing customers, certainly we're looking at drug discovery places. We do actually have one activity, important activity, with a bank, like you said, on a case of portfolio optimization. So you are spot on in your mentioning of this. We're also looking at, I would say, autonomous applications of, it's related to, suppose you have a lot of autonomous, say, vehicles or aerial devices working together, and they interact with each other, and they need to understand the paths that each other is about to take in order to, in order for them to take their own path. So this is a very difficult and important optimization question. So we have another customer which works on this. To give another field, we are also starting to work with a customer on complex areas of chip design, of classical chip designs. There are a lot of very deep optimization questions. And we also always go into the direction of where it's not only a difficult optimization question, but an optimization question which is critical for the business. So if you can think of a chip designer, it is critical for the business that this company will be able to put more and more units, including the wirings, etc., on the chip. So once you have an optimization problem that is, one, very hard, and two, critical for the business, this is typically where we aim.
Mm-hmm. And how is it happening? Let's say customers trying to find you, or you try to talk to companies, so you find them on the conferences. How do you find your first customers?
Yeah. Okay, so as I said, the community is very, very open, so we all know about each other. It doesn't have to be a quantum company, a quantum department within some company. We will know about them, and we just discuss, like you say, well, now it's on virtual conferences in Zoom, but still we get to know each other. But between the two, your first option was much more correct. People hear about us. People are very thirsty. They are very in need for ways to help their quantum developers do what they ought to do, design algorithms, and they hear about us. They hear about us that we are able to deliver, and they approach us. And then we have the difficult task of defining with the potential customer whether the problem is important enough for their business in order for us to decide whether we work for them.
And then pretty much you start developing, let's say, first algorithms and how to approach this problem, right? Because creating these algorithms is quite complicated.
Yeah, so typically we expect our customer to know, to understand what they want, not only in terms of the business, but also in terms of of the quantum algorithms, to have an idea of what they want, but to know that their direction is very difficult to implement for themselves. They need an automation tool, they need a synthesis tool to translate their thoughts into a quantum algorithm. This would be our perfect customers, and this is what we aim for, and this is what our customers typically have. They have a quantum group. They know what they want, but they know they cannot do it by hand. They need some form of deep technology which will translate their algorithm design into a concrete circuit. Just as you would expect in classical computer, you don't expect anyone to write down assembly code. It's the perfect analogy here.
Yeah, and of course, right now we're talking about quite complicated algorithms. So you think that the person, even if he wants to formulate the algorithm, the question, he still needs to know some basics about quantum mechanics, because not all questions could be addressed, let's say, with quantum computers, right? So the person who wants to formulate the problem and give it to you, he or she should know at least something about quantum computers, right? And what they can do and they cannot do.
Yeah, that would be ideal. That would be ideal. And they probably need to know, the high-level concepts of quantum computing, saying entanglement, superposition, interference, destructive interference, and things like that. They need to know what a qubit is. They need to know what a quantum register is. Whether they know it in advance or, get acquainted with it on the job, This depends. Typically, a quantum computing department would have one or two experts which come from the field, some recruitment of the company, but a lot of people around them, which maybe, computer scientists or programmers, which have a very strong passion to learn a new thing. And from my experience, it is possible to learn the high-level aspects quite rapidly. If you have the passion and have the motivation, I've seen this happen a lot.
And maybe you have some hints how to understand if the problem is good for quantum computers. Because let's say the company is working on some problem and he said, oh, I've heard the quantum computers, they're good, they can do cool stuff, they can do it fast, exponential growth, bam, bam, bam. But the question is like how to understand if this problem is particularly good for quantum computers.
Okay, so many problems are already known to have quantum heuristics. And then it is simple. It is only to translate your actual problem, your actual typically optimization problem, into a known problem which already has a quantum heuristic solution. By the way, to be a little bit technical, when I say quantum heuristic solution, I mean things like variational quantum algorithms, or sometimes people call it quantum approximation optimization algorithms, and so on. Once you can translate your problem, your business problem, into one such problem, then everything is easy. The heuristics were already done. It's just a matter of now doing the heuristics much better for your particular case. There are other cases, sometimes even for machine learning. A lot of people want machine learning solutions. Well, we are still at the study. Machine learning is even difficult from an algorithmic point of view, even in classical computers. I mean, some heuristics works, but no one can prove them. So in such, groundbreaking areas, places where we still don't have the proven heuristics, then the problem is challenging of understanding whether it's worthwhile, to invest the effort, because maybe we will find a solution and maybe we will not.
Yeah, and maybe I want to ask another question which is related to the company D-Wave. Maybe you know that there is like people arguing, is it really a proper quantum computer? Or is it like universal quantum computer? But these computers get powerful. Can we use these computers to address some problems?
Okay. So I feel that this type of questions about, well, I wouldn't say, I don't want to call companies by names, but about annealing approach to quantum computing, I personally feel that this is a question of the past. In the past, it was worthwhile asking whether it is real quantum or not real quantum, whatever that means. I think looking into the future, I think that the advancement in gate-based quantum computing or universal quantum computing, in whatever way you want to call it, is much more, there is much more clear. The path into the future is going to be through the advantage of universal gate-based quantum computing. And I think that looking, some years into the future, companies which do quantum annealing will need to move a little bit, not that much, but move into what everyone else is doing, universal gate-based quantum computing. I'm saying it's not that much of a shift for those people because even quantum annealing is implemented by qubits. So I think my impression is that there is not going to be a real, advantage of going further with annealing.
Mm. And maybe right now, let's move to a bit of speculation and talk about how will things develop in the future, what we can expect. Probably we can speak about, you already mentioned some, let's say, timestamps, what we can expect and what type of qubits. So you mentioned that we want to have, let's say, 1,000 qubits, right? And then we can address decent algorithms. So, and which time do you think it will happen?
So if we look just, for example, at the technological roadmap of IBM, so we are about to have like 1,100 qubits working coherently on a chip in 2023, if I remember correctly, which means 2.5 years from now. From what we've seen in the past, the actual technology moves faster than the predictions. So I would not be surprised to see 1,000 qubits on a chip in late 2022 or early 2023. And I want to stress here that these are not predictions by some marketing persons in a company. Those are technological predictions, and people who who historically remember the silicon industry roadmaps know that those predictions are actually a work plan. So if like Moore's law is not there by default. Moore's law came into being because there was a consortium of all semiconductor manufacturers which decided that 2 years from now we will have this technology, 4 years from now that technology, and so on and so forth. And everyone, all companies abided by those standards. So we're starting to see the same here. The technology companies provide a roadmap, and as long as there are not any fundamental physical barriers in implementing this roadmap, this is what we're going to see.
Yeah, I agree. I think like once company make a statement, they probably have to address it and keep processing. And now I want to ask about new fields, because with quantum computers, we have new fields which are raising, let's say, quantum machine learning. And I want to really understand how much, let's say, real development is here, because sometimes I feel that some new terms appearing, and I'm not sure there is much technology behind it, because I'm not really expert, but when I hear quantum machine learning, to me it sounds too complicated. What do you think about quantum machine learning?
Yeah, so obviously it's first of all a catchphrase, because everyone talks about machine learning and everyone talks about quantum. So obviously it's a catchphrase. Let's just combine the two and call it quantum machine learning. After saying that, if we look into the details, there are some nice technical works in this field. Some of them are related to what I said earlier about HHL algorithm, Haram Hasidim and Lloyd algorithm. As you know, in many classical machine learning algorithms, the workhorse is just solving linear equations. And if you can transform your machine learning problem into sparse matrices, then you can immediately use a proven algorithm, a proven quantum algorithm, which will provide you an exponential speed up. So this is one set of works. Another set of works is dealing with the inputs into the algorithm, where if you can do it quantum mechanically, you can save a lot, because you can input a vast amount of data as a superposition of all your data. So this is another approach which is quite futuristic. It's not going to happen, not tomorrow and not next year, but there is some sense to it. And then there are a lot of approaches which are heuristics. And this is the place, again, to remind ourselves that many of classical machine learning algorithms are heuristics, are not proven, and still they work. And if classical heuristics works, then there is a strong reason to believe that in some cases, quantum heuristics may truly show an advantage, show a benefits. So nothing proven here. This is the nature of heuristics, but I myself personally believe that in places which are very difficult and where classical heuristics do not work anymore, quantum heuristics, which have a very different flavor to the way they search over space, may certainly work.
Yeah, and I think, let me ask maybe my last question, which will be a bit of personal. Sometimes I feel in social media, sometimes when I'm reading a lot of posts and blogs about quantum computing, I hear a lot of, let's say, inflated statements which are not supported by any development. And so I'm following a few people, I wouldn't mention names, but I feel like these statements don't have any background or any development. So what do you think about these inflated statements in terms of quantum computing? Because some people think that there is a little bit of hype here, you know?
Yeah, so a little bit is, of course, an understatement. So I cured myself from this in just that I stopped reading any social media or any blogs or anything, except where I feel that it comes from people that I know that they would not sacrifice their name and prestige with nonsense. So I just prefer not to read things just because they are written, and I prefer not to read, anything that is written down, because I totally agree with what you are saying. But still, that I take the position that even though there is a lot of hype, it does not mean that there is also not a lot of technological merit in the real things. So I try to read the real things. I try to read people from which made the right statements in the past. I try to read things from people which back up their statements by proofs, by numbers, by reason, and that's good for me. There are a lot of people, a lot of good people, a lot of scientists who still tell us the truth, and I just try to ignore everyone else.
Yeah, I agree. I think it's a good approach. You have to choose wisely with who you listen and with who you talk. It was a very
This is the same everywhere today, right? Not
yeah.
only in quantum computing.
Yeah, that's true. That's true. It was my real pleasure talking to you. I learned a lot from our discussion. It was really nice because I really enjoy talking, especially to quantum software developers, because I'm coming from the experimental point of view or hardware point of view. So for me, it's always nice to learn what's the development. So thank you very much for taking your time and talking to me.
Sergey, thank you so much. I enjoyed it so much as well, and I truly appreciate and thank you for having me here with you today.